Hey guys, BuildZoid here, and today we're going to be doing a B650E motherboard PCB breakdown, the ASUS Strix B650E-F gaming Wi-Fi motherboard. Now this board was sent to me by ASUS, so big thank you to them for providing it for testing. I've not actually tested the board yet, but I have taken it apart, as you can clearly see from these photos. So we're going to be taking a look at sort of the hardware that makes up the board. But this is not a review because, again, I've not done any testing. I just like looking at power delivery circuitry. And then for some reason, I've also been slowly pushed by my comment section into talking about things that I don't care about, like M.2 slots. So, this being a B650E motherboard, you get a Gen 5 M.2 slot over here that's connected directly to the CPU. You also get an X16 PCIe slot that's Gen 5 connected directly to the CPU. Then you get this M.2 slot down here, which is Gen 4, also connected to the CPU. And then you get this M.2 slot down here, which is Gen 4, but this one's connected to the chipset, and it shares the, well, it doesn't share the PCIe lanes. It uses the same PCIe lanes that this X4 PCIe slot down here uses. So you can either have this Gen 4 M.2 slot, or you can have this Gen 4 X4 PCIe slot. You can't have both of them at the same time, because like the way this is actually set up, and you can kind of see it on the board right here, is the PCIe lanes go from the chipset into this PCIe switch, and that either sends those lanes, like you either send those lanes to the M.2 slot, or it sends them to the PCIe slot. It can't send them to both. So yeah, anyway, so that's the PCIe connectivity that you get internally on this board. Kind of like there's B650E motherboards that offer more internal connectors than this, but at the same time, the B650E chipset is actually very limited in terms of like connectivity. So this is kind of like this is basically what you can do without adding like expensive extra chips to sort of compensate for the lack of I/O on the B650E chipset. Anyway, you do still get 4 SATA ports internally over here, and there's also an internal Type-C header up here. And that basically covers all of the more noteworthy internal connectors that this board has. So let's move on to some of the overclocking features that it comes with, which is basically just some color-coded troubleshooting LEDs over here. If this were an Intel motherboard, I'd be quite upset that this isn't a postcode, but this is an AMD motherboard, and AMD motherboards, the postcode doesn't tend to be that helpful, so while I still think it would be better if this were a postcode instead of, just color-coded LEDs, it's not as much of a loss as it would be on an Intel motherboard potentially, because on Intel motherboards, especially if you're doing a lot of memory overclocking, like there's a few different postcodes that you can get stuck on that indicate like different issues. Whereas in my experience with AMD CPUs, any kind of memory problem ends up on the same 2 postcodes. So, like basically it's the equivalent of just getting stuck on the DRAM LED. So yeah, and that like it's not as much of a it's not as much of a downside as it would be on an Intel board to just have trouble like color coded LEDs. And being color coded, it'll be much easier to tell what's wrong than there are some other boards which uses the same color LED for all of these troubleshooting LEDs, and then that gets really annoying when you sort of need to figure out which LED actually lit up in order to figure out why the system isn't posting. So I do like the fact that these are color-coded. Anyway, there are other overclocking. It's not really features, but there are other overclocking-related things. So we've got a CPU overvoltage jumper down here, which is basically an idiot-proofing thing. The BIOS won't let you set insanely high voltages unless you move that over. I'm not sure what the voltage restrictions are out of the box, but like if they're too low or something, ASUS could always tweak them with like a BIOS update. Anyway, other than that, there's also a clear CMOS jumper down here, which you might want to wire up to your case's reset switch if you're doing a lot of memory overclocking, because Ryzen's automatic overclocking recovery, in my experience, is extremely flaky. On some BIOS versions it works, on some BIOS versions it doesn't work, and sometimes the best BIOSes don't have like best memory overclocking BIOSes, as in you can do the best settings and you can get the best performance, don't necessarily have the best auto recovery functioning at the same time. So yeah. Anyway, that kind of covers it for internal, like, well, overclocking features and internal connectors. Like, it's a B650E motherboard. It's kind of, and it's not a top of the line B650E motherboard, so it's a bit limited on the uh, internal functionality and overclocking functionality as well. But anyway, let's move on to the rear I/O, where we find a bunch of USB Type A ports, Intel 2.5 gig LAN, Wi-Fi 6E, two USB Type-C ports. ASUS decided to sacrifice the optical audio output for one of those Type-C ports. So if you need optical audio output, yeah, you're kind of screwed with this. But if you just want the regular analog audio ports, you've still got all of those. There's also a BIOS flashback button, so you can update the BIOS of this motherboard without even having a CPU installed in it. And this can potentially also recover from like BIOS corruption. That's not its intended purpose, but if you do, like, if your BIOS gets corrupted for some reason, it can potentially recover from that, which is pretty neat. Not that that's really a very common issue. In fact, that's an extremely rare issue. Like, I see a lot of people always go like, "Oh, it's a BIOS problem." Most issues are not BIOS problems. So, though that's usually people like speculating about like repairing a GPU that very clearly does not have a BIOS issue. But anyway, so yeah, in terms of rear I/O, like, I like it mostly because there's a lot of Type A ports, and I'm a sucker for USB Type A ports. Like, they could have maybe added two more, and that's about it. Like, there's not, they're kind of running out of space. So anyway, that's the rear I/O, and let's move on to the actual power delivery. So you do get a 8-pin and a 4-pin power connector. The 4-pin is entirely optional because there are currently 0 CPUs that you can install into the AM5 socket that will overload an 8-pin. Yeah, like, having both of these plugged in makes 0 difference to the VRM's ability, because, like, the voltage regulation, because the VRM can account for like a voltage drop. Like, it really, like, if the voltage is, a bit low, the VRM can deal with that. It's designed to deal with that. That's not an issue. So plugging this in really is just a matter of, like, if you have a CPU that pulls well north of 300 watts, which even a overclocked 7950X doesn't, you would want to plug in the extra 4-pin. But no such CPU for AM5 exists, so this 4-pin is entirely optional. If your power supply doesn't have the extra connector, you can just ignore it, because it doesn't do anything. It definitely doesn't improve your overclocking. Anyway, ASUS did opt to use the high current variant of the power connectors, which you can tell because the pins are solid. For comparison, they use the standard current rating folded metal pins on the 24-pin power connector, and you can see the difference, right? Like, you can see that this is like a metal tab, and then the rest of the pin is just a piece of metal that's been folded out into the plastic connector, whereas this is a metal sort of like rectangle. Not a rectangle. It's not a cube. I've forgot the name of that. It's not even a shape. Yeah, I've forgotten the name. But anyway, like, these are a solid metal pin, whereas these are a piece of flat metal that just got folded into the shape of a pin. And that's why you see like the little tab coming through the back, whereas these have a more square shape. To them. So yeah. Anyway. And also, the reason ASUS is opting for the like folded metal pins for the 24-pin is because the 24-pin really shouldn't be handling large amounts of current, so there's no reason to use the high current variant of the power connector on the 24-pin. Also, when it comes to unplugging the 24-pin, it's a lot easier with the folded metal pins than with the solid metal pins. So, if you're swapping motherboards a lot, this is actually kind of nice. Anyway, let's take a look at the actual voltage regulator. So the main CPU power delivery is all of this over here. And that's split up like this. So this portion right here is for the SoC power. And then this lower half, well, yeah, I guess you could say lower half and upper half are all Vcore. And all of this is controlled by this chip over here. And that chip is a ASUS branded ASP 2208. And I unfortunately have no idea who makes this thing. It could be Renesas. If this was literally any other manufacturer, I would assume that this is a Renesas chip. But this is ASUS, and ASUS in the past has been willing to use pretty much any manufacturer, like any. Well, no, I don't think they ever mixed international rectifier controllers with non-international rectifier drivers. So, not that, but if I remember correctly, they did mix like Richtech controllers with like Vishay power stages on like Z390. Now, this almost certainly isn't a Richtech VRM controller because I don't think Richtech makes anything that goes above 4 phases. And as far as I can tell, this is running as a 6+2 phase. Yeah, but so I'm like, it's probably a Renesas part, probably, but I really like, I don't know. But I don't know for sure. But yeah, so that's kind of annoying. But ultimately it doesn't really, like, it doesn't really matter that much to know exactly who made the controller. So, because the thing is, like, a very important part of the VRM design is actually the configuration of the firmware for the VRM controller, and ASUS generally does a pretty good job of that, or at least a consistent job of that. Some of the other manufacturers, some have, like, wildly varying performance, with some motherboards being absolutely incredible, and some other motherboards in, like, the same generation of product being, like, the worst thing I've ever tested. Yeah, it's kind of that. Whereas ASUS, in my experience, will generally perform really, like, will often have some of the best performance, and it'll be pretty consistent. Like, even the low-end boards will have properly set up VRM firmware, which mostly just comes down to not having ridiculously aggressive load line calibration settings, which occasionally happens, or having functional load line calibration settings in some cases. But yeah, anyway, so it's a bit annoying that we don't know who the manufacturer is, but in terms of actually being like useful information, it's not really, it doesn't really matter that much, because without testing, like, who made the controller is borderline irrelevant. So, well, yeah, borderline irrelevant. It's just kind of, it's more of a nice to know thing than need to know thing. Anyway, let's take a look at the power stages, which unfortunately are more like not very detailed, like not very information-rich parts. Oh, and I guess I should have mentioned that this being a 6+2 phase VRM controller setup, we do have 2 power stages in each phase of Vcore. So like this is a phase, that's a phase. Well, should be saying that's a phase, that's a phase, that's another phase. Then you've got a phase here, phase there, and so 6 phase in total. And ASUS is just running one PWM. Like, there's no doublers or anything on the back of the board because, like, it's an ASUS board. And actually, these days, nobody really uses doublers. I've been kind of wondering about why the VRM manufacturers even use doublers in the first place. Because, like why the VRM manufacturers even made doublers. Because, like, that's the thing, is, like, when you buy doublers, they're, like, you'd have, like, an intersil controller with your intersil doublers for your intersil power stages. And it's like, as far as I know, the whole taking a single PWM signal and shoving it into 2, power stages at the same time, that's actually been around for a very, very long time. And I think MSI was the first manufacturer to ever do it, because they were using a controller which, while it did offer the option for doublers, those doublers couldn't double hard enough for what MSI wanted to do with them. So they were just kind of stuck with not quite as many PWM signals as they wanted, and they ended up just shoving one PWM signal into 2 power stages to get to the total number of power stages that they wanted. But yeah, like, these days on a lot of motherboards, it's just standard to take a single PWM signal, shove it into power stages. There's really no downsides to doing that, which is why I'm so confused why the doublers were even a thing. Funnily enough, some of the old doublers, well, actually, no, it's not that confusing. Some of the doublers did offer like current balancing, so you could potentially get slightly better efficiency out of the VRM with like ideal current balance between the two power stages. Whereas in this configuration, you just kind of have to hope that the thermal, like the power, they're just going to kind of current balance themselves, which they will. Because whichever power stage is running hottest is going to probably end up with the slightly higher on resistance, which means more of the current is going to take the path of lower resistance, right? So if you have 10 amps flowing through one phase in total, um, or let's say you have like 20 amps flowing through the phase, you'll have a split like say you might end up with a split like 11 amps over here because this power stage is running slightly cooler than this one, right? Because this one's right next to more power stages, so this one's going to be running a bit hotter. So this one might be handling only 9 amps of current. And that'll actually potentially work out just fine. And like that won't actually affect your efficiency. Whereas if you had a doubler, you could like force the current to be equal on all of your power stages, which might, like, depending on the scenario, might give you a very slight efficiency advantage. And so yeah, I'm honestly kind of confused, like why we even had doublers in the first place at this point, because it's like the putting the PWM signal into two power stages at the same time. That's not a new idea by any means. It's just only recently become a popular idea, and ASUS is is the manufacturer that popularized it. So, you know, I guess they deserve some credit for that, because at the very it's it makes high power VRMs a bit cheaper to make. Not that you can really tell from the pricing of current gen motherboards, but yeah, the power delivery is a bit simpler to implement, and well. The thing is, now we have more expensive power stages, so anyway, let's talk about what these power stages are. And unfortunately, these are SIC 659s, which these are, according to ASUS, 80 amp smart power stages. And the reason I say according to ASUS 80 amp smart power stages is because these are from Vishay Semiconductor, and there's no public documentation for them whatsoever. So these are from Vishay. And the thing is, Vishay doesn't have anything in their parts catalog that like is similar to these other than like 60 amp parts. Because this is a 5x5 millimeter power stage package, and Vishay, for all of their higher current parts, and they have some like 70, 80, 90, 100 amp part. Actually, they even have 110 amp parts. Those are all in a 5x6 millimeter package, not a 5x5 millimeter. So yeah, I have no idea. Like the problem with the nominal current rating for power stages, and this is true for all manufacturers, is that once you go past 60 amps, the performance differences between the power stages become kind of difficult to distinguish. Like if you have a 35 amp power stage, it is definitely worse than a 40 amp power stage. Like there's no debating that. It doesn't matter what manufacturer made that 35 amp part, it is worse than a 40 amp part. Like that is very consistent. The same is true for like a 50 amp part versus a 40 amp part. And the same is still true for like a 60 amp part compared to all of the other things that I just mentioned. But then you get to the parts rated for over 60 amps, and that's when you start noticing that like a lot of the way this nominal current rating is achieved by each manufacturer, there's like different methodologies, how they arrive at that rating. And so it ends up being a case of like, as far like potentially some like 90 amp parts are actually like better than like 100 or 110 amp parts. And then you have like 70 amp parts that also perform very differently depending on which manufacturer they're from. And so, or well, very differently. Like differently, like no differently enough that it's noteworthy, but not so different that you wouldn't like it's not like they're worse than 60 amp parts, that kind of thing. So yeah, I like whenever I see these really high like nominal current ratings for power stages, I'm not like they're not good numbers, okay? Like this isn't like, oh, it's a 60 amp power stage, it's just better than everything rated below it. It's like, oh, it's an 80 amp power stage. what does the performance curve look like? Because there are 80 and 70 amp power stages out there which have basically the same performance curves as 60 amp parts. And at that point you might be wondering, but why are they rated for 80 amps then? Well, usually it'll be something like the overcurrent protection being set really high so that you can handle like 80 amp burst current. Like the power stage won't just shut down on you if you try to push 80 amps through it for a short period of time. And the reason this rating over here is really not that helpful is that no matter how it like peak efficiency for power stages is around 95%. If you're pushing 80 amps through a 95% efficient anything, it's going to kick off a lot of heat. Okay? And when that heat is concentrated in a 5 by 5 millimeter square, it doesn't tend to go very well, especially if you have several of them next to each other. So that's why this like nominal current rating number, like this is more of a like a performance class thing than an actual usable performance metric, right? Yeah, that's sort of the best way to look at it. But anyway, so since I can't actually get any useful documentation for SIC 659s, or actually like these don't even exist on Vishay's website, there's no mention of them, so this is probably some special order part for ASUS again, I went with what I would consider the next closest thing, which is the SIC 645. Which is a really good 60 amp smart power stage. Also, these Vishay 60 amp, well, these Vishay smart power stages in this 5 by 5 millimeter, well, this is the thing. The 645 integrates a bunch of really cool features like high side MOSFET short circuit protection, then also your standard stuff like over temperature, over current protection, under voltage lockout, which basically just means if the like supply voltage for the power stage gets too low, it'll turn off. It won't like brown out, it'll just turn off. So, yeah, like but I'm not like, the thing is, I'm not entirely certain that these are rebranded. Like these could be like a special variant of a 645, but I'm not 100% certain. So these could have all the same functionality of the 645s, in which case that would be really, really cool, especially the high side MOSFET short circuit protection is a really cool feature that some smart power stages have, because when a VRM fails, typically the MOSFET that fails hardest and also is the most dangerous to everything downstream is the high side MOSFET, because when your high side MOSFET short circuits, you basically connect 12 volts straight to the output of the VRM, and that potentially means your CPU goes bye-bye. It can blow up all of the output capacitors. You can, like, depending on how slow the rest of the system's overcurrent protection is or short circuit protection is, you're going to have a bad day or a really bad day. So yeah, like these might have all the functionality of the 645s, but I don't know, because these literally don't even exist on the Vishay website. But I would assume that they perform at least as well as the 645s, if not better. And so for the VRM efficiency estimates, I've gone with the 645 numbers instead of, well, non-existent 659 numbers. So at 1.2 volts output voltage and 500 kilohertz switching frequency, that's not a very good 500 kilohertz switching frequency, this VRM should be able to output 200 amps of current while producing only about 17 watts of heat. So yeah, it'll have absolutely no issues handling a 7950X, because the 7950X has this, like at stock, has a 160 amp current limit, and even if you're overclocking, getting that chip to pull over 200 amps is extremely difficult because it gets very, very hot. So, yeah, you don't really, like, this VRM will have no problem powering any CPU that you can put into this motherboard. Honestly, it wouldn't even have any problems with, like, LN2 overclocking, potentially, if you wanted to do that. I think the bigger concern for LN2 overclocking with this motherboard is the fact that you won't have a postcode. So when the system doesn't want to turn on, you're going to have a really unpleasant time figuring out why that is, because on LN2, things are very different from on ambient. In terms, like, on a lot of platforms, getting the system to turn on while on liquid nitrogen is actually a challenge, especially on like a lot of the Ryzen CPUs. So, yeah. Anyway, 300 amps output current, the VRM would only produce about 28 watts of heat, and 400 amps of output current, it would produce about 47 watts of heat. And from this, you can also kind of see why, this nominal current rating multiplied by how many power stages we have, because we have 12 power stages here, and this is 80 amps, so you'd be like, oh, it can handle 960 amps. Well, at 500 amps output current, the VRM would produce about 66 watts of heat. And at this point, you're, that is kind of a lot of heat to deal with. So that's kind of the issue. And this, the thing is, like, you'll notice that the difference between these numbers keeps getting bigger and bigger, right? Because, like, this is an increase of 11 watts, and going from 28 to 47 is what, like, 19 watts? And then going from 47 to 66, we're going up, what, like 20? Also 19? Oh, I guess that's in the... That got into this part of the curve. Yeah, of the efficiency curve. And anyway, the thing is, basically, as you keep going up in current, the heat output goes like this. So by the time you get to 80 amps, this kind of VRM would be producing easily over 100 watts of heat. And yeah, that's not practical to cool, which is why the nominal current rating is very misleading. You can't just take this number and multiply it by however many power stages you have, because you will, technically, if you had water cooling on your VRM, it would actually be doable. Practically speaking, that's a terrible idea. You should just design a better VRM, if that's what you're trying to do. Anyway, yeah, but for any, for practical concerns of the, AM5 socket with the CPUs that are available, this will have no problem powering even the 7950X, even with an overclock. So, yeah, this VRM is... the thing is, I don't want to say overkill, even though it technically probably is, because we have a bunch of AM5 motherboards which have even more substantial power delivery, and then what are those? Right? We just end up with yep, every motherboard is now overkill, which I guess is fair enough, because even the cheapest X670 motherboard that I tested could power a 7950X without the VRM heatsink installed. So yeah, I guess that's kind of that. Anyway, so yeah, Vcore on this is overkill. And for the SoC VRM, we've got more of the same power stages, and the SoC VRM has to supply very little current. So this is kind of the Vcore here is kind of overkill. This right here, extremely overkill. You do not need two 80 amp smart power stages to power the SoC portion of the Ryzen 7000 CPUs. That's just totally unnecessary amounts of overkill, but that's kind of the norm for the SoC power delivery system. Because the thing is, once you've already bought these power stages, well, you may as well just slap them into the SoC VRM instead of adding a different component to the bill of materials for the board, right? So yeah, that's how that happens. It's not going to change the cost of the board that much at that point. Anything else I wanted to mention? Oh yeah, the layout's a bit weird. Most other motherboard manufacturers put their SoC VRM over here. And historically, the reason why ASUS started doing this SoC VRM sort of mixed in between the Vcore phases was that it would help reduce the thermal density. Though in this configuration, I'm kind of questioning whether that's even the case, because all of these Vcore phases are right next to each other. These Vcore phases are so far away from this that I don't think this makes a difference. If the SoC VRM was I don't know, here or here, I'd kind of get it, right? Because you'd have one group of very hot, because these power stages are handling more current than these are, and these power stages would be handling more current than these are. And then it's yeah, okay, that sort of splits up the thermal density a bit, but that's not what we're looking at here. So I'm really confused why they didn't just do what everybody else does and shove the SoC VRM over there, because the actual SoC, as far as I know, is located right over here, and your CCDs are down here. At which point you might be wondering, why is most of the Vcore up there? Well, there's not really any space down here. Like, you need to run PCIe lanes in this area, and yeah, you don't really want to be doing that. Well, you don't want to be trying to run PCIe lanes under the power delivery, because the switch node of a VRM phase is very, very noisy. So you kind of want to keep all your high-speed sensitive signals very far away from the VRM. Anyway, or at least as far away from the VRM as possible, right? So that's why you generally don't put it right here, because then your PCIe lanes need to deal with the fact that the VRM exists. But anyway, so that's the sort of main CPU power delivery. Then down here we have the VDD MISC rail. This is a nice, simple, just integrated buck converter from Max Linear. So this is a MXL 7630S. I remember, yeah, that's the 7630S. This is a 30 amp buck converter. Probably can't do 30 amps all on its own, though it is sharing the the heatsink with the Vcore VRM. So yeah, and also the VDD MISC rail only powers like the built-in voltage regulators for the Infinity fabric. So this really doesn't have to output a lot of current. And yeah, so that's why ASUS opted for like such a simple VDD MISC VRM, because it's just like it doesn't need to output a lot of current. So why go with anything expensive and complicated? Anyway, so that's VDD MISC, and then the last sort of like noteworthy, like, because there's other regulators, like I think this is a linear regulator for maybe something like 1.8 volts that goes to the CPU, and then we have another seemingly linear regulator over here, right? So there's other minor like supporting voltages that the CPU socket gets, but we're not going to be tracking all of those down. But the next big noteworthy voltage regulator is this thing right over here, and that is the VDDIO MEM. And this is basically a DDR4 memory VRM, except unlike with DDR4, it doesn't actually have to power the memory sticks. So the reason this exists is you still need to supply power to the memory controller so that the memory controller can talk to the RAM. But the RAM itself has its own built-in voltage regulators, right, on the memory sticks. And so we no longer need like this VRM that previously had to power both the memory sticks and the memory controller now just powers the memory controller. So it needs to do a lot less work than it used to, but ASUS decided to basically use the exact same VRM design that they've always used for their memory power, which is a set of low side MOSFETs and high side MOSFETs. So you have two high side MOSFETs, two low side MOSFETs. And these MOSFETs are all on semiconductor 4C10Ns. In any other application, I would complain. Well, actually, that's not true. There are other valid applications for these MOSFETs, but there are motherboards that use these in their Vcore VRM. That's bad. For memory power, these are perfectly fine. Yeah, so we have a bunch of 4C10Ns and it's not even really memory power. It's like memory controller power in this case, which is even less power draw than like the old DDR4 memory power. But anyway, the chip that's actually like controlling and driving those MOSFETs is a Richtech X6 equals 9B. I'm assuming this is like Richtech has just the wackiest like part like code numbers, because I suspect this is an RT8120. Which is like a super common single phase built-in drivers, like VRM controller with built-in drivers. You see it on a bunch of gigabyte motherboards, but it's not this small. All right, it's usually it's about the size of. Is there not? Do we not have one of those chips? Oh, it's usually about the size of one of these, right? Which is a bit inconvenient because that's an awful lot of board space to use up in this sort of crowded part of the board. So yeah, and when Richtech has to shrink their parts, for some reason they resort to these like super obscure labels, which you can't even reliably search on their website, which is why I didn't bother to dig through Richtech data sheets until I found one that, mentioned this label. But yeah, I think it's probably an RT8120 of some kind. and it just has a wacky label on it because it's in a reduced size package. The funny thing is, I'm pretty sure like X69B and RT8120 takes up about the same amount of space, so I'm really not sure why they do this. Right? Like this isn't exactly a shorter version of the usual part number that like larger Tech chips have. So, yeah. Anyway, Tech is just weird like that. And you can recognize them because they like to do this equal sign thing on a lot of their chips. Actually, I think they're the only manufacturer who puts equal signs into their like chip labels. So, yeah, that's fun. At least the only one I've seen. So yeah, that powers the memory. Now then, I do actually want to talk about the capacitor configuration on this board. A lot, a little, kind of a lot. So this capacitor belongs to the VDD MISC rail, so we're just going to circle that one off. Like this bulk capacitor over here. These belong to Vcore. Yep, those belong to Vcore. So those belong to the Vcore VRM. These belong to the SoC VRM. And really the most noteworthy thing for me when sort of I started taking apart this board was this right here. This is like, I've not really, this isn't rare for ASUS motherboards to have like extra output filtering capacitors rammed right up against the CPU socket, especially on AMD platforms. They have been doing this for years. There's like AM3 Plus boards from ASUS where you just have extra multi-layer ceramics hanging around the CPU socket area. And the idea behind this is like you want to get the filtering capacitor, like ideally you want the filtering capacitors on the same layer as the actual LGA, like the pins in the socket, right? Because VIAs add some extra inductance. Like you want to get the capacitors electrically as close to the CPU as possible. And so to do that, ASUS sort of, puts these like sets of multi-layer ceramics just right up against the CPU socket. And they opted to not include these for some reason. I'm kind of surprised that they even bothered with this board. Like, I'm not necessarily surprised that like there's unpopulated padding, but the thing is, I first noticed that ASUS is doing this on the Crosshair Gene, the X670 Gene for AM5, and I didn't think that I would see this on a, like a Strix board. I really didn't expect to see it here, but yeah, it's cool that they've decided to include this. How much did this improve the voltage regulation? I'm really not sure. The only way that you could really test that is to like take measurements with the capacitors in place, then desolder them and see how that changes. I don't think I'll be getting permission to do anything like that. I don't even really want to do anything like that because, so on one hand, I wouldn't necessarily be too surprised if it made no difference, but if it made the board significantly worse, I'd be annoyed, because then I'd have to like get the capacitors back on there. Anyway, this is for memory actually, which is still really cool. Like there's just a bunch of extra filtering that ASUS put on the top layer. Like this belongs to VDDIO. This is also Vcore. This right here is SoC, and it's not quite like, these are larger capacitors, so these have more equivalent series inductance than these like smaller ones that they've packed over here. Though I kind of suspect that they use these small ones because they wanted to fit them under the hold down bracket more so than because of their, well, you can get half height 0805s. So, maybe they did go for it for the lower inductance. Well, yeah, especially if you're like putting, groups of 6 of them at a time. Like that'll give you even lower equivalent series inductance because you have a bunch of capacitors in parallel. But yeah, so like I just think it's neat that ASUS does like these little, output filter details, basically. How effective they are, it's really hard to say. Actually impossible to say without measurements. But yeah, and the reason I think it's neat is like they also pack the, allocated CPU socket cavity for, because like the whole point, like the reason you get this cutout in the backplates, and you see this on all motherboards, is like this is where you're supposed to put a bunch of filtering capacitors for the CPU power, right? And that's exactly what ASUS is doing. In fact, they've packed quite a lot of multi-layer ceramics. There's some AM5 motherboards that don't go quite so, that aren't quite so populated on the back of the board like this. And And yeah, so like ASUS, fills out the socket cavity quite a lot. It's not completely full. I don't know if that would even be practical, right? Because like we can kind of see, I think, bits of the CAD bus running. Yeah, it looks like we have some CAD bus traces going in this area. So you probably like wouldn't necessarily like you need the space for things like your memory command address bus. So you can't just fill everything with capacitors because I think we also might have some PCIe lanes coming out in this area. So yeah, but they've, packed the CPU socket. Well, it's not really a CPU socket cavity, but like they've packed the back of the socket quite heavily with multi-layer ceramics. Um, and then on top of that, they also have these extra multi-layer ceramics around on the top side of the board. And the thing is, normally the AMD like design, like the AMD sort of motherboard requirement is just this part. Like the extra capacitors that they have on the top layer of the board, like those are entirely like an ASUS idea. There's no like requirement for those from AMD as far as I know. So yeah, I think that's neat that like ASUS really is putting a lot of ceramic onto the CPU power delivery, because ceramic capacitors, like they just have less inductance and ESR than your through-hole capacitors. So yeah, if you can get them as close to the CPU, that's a good thing. Anyway, for the bulk capacitors, these are rebrands again. So they're branded mil for like military standard, right? Because motherboard marketing. But these are 5,000 hours at 105 degrees, as are all of the other capacitors on, like all of the other polymer capacitors on this board. And these are solid polymer capacitors. So if you're thinking, oh, that 5,000 hours at 105 degrees Celsius, that doesn't sound that long. What you need to understand about solid polymer capacitors is that this just indicates when they lose, I think it's 20% of their ESR, something like that. Like this, they're not dead after 5,000 hours at 105 degrees. In fact, they're still very functional after 5,000 hours at 105 degrees. So yeah, like this, and that's assuming that they're actually, running at 105 degrees. So yeah, like with solid polymer capacitors, because the reason I bring that up is like, yeah, there's some motherboards that have like 10,000 hour rated capacitors. Doesn't really make a difference. Like these are solid polymers. They don't really, like, they're not going to leak anything because they're solid. That's kind of the point. And after 5,000 hours at 105 degrees, like they're still very functional. So yeah, anyway, as for the other specifications, these are 6.3 volt capacitors, which is what you typically see in the output filter of a motherboard's like CPU power delivery. And the reason they're rated for such a high voltage is because there's 5-volt rails running around the motherboard. So like here, like say the memory VRM over here, that typically runs off of the 5-volt power from the PSU. And so you just use a 6.3 volt capacitor for, input filtering. And then you'll have like a 6.3 volt capacitor over here for filtering the power for the USB ports. And then you have like a 6.3 volt capacitor over here for filtering the power for the PCIe slot. And so if you're using these, 6.3 volt capacitors just sort of all around the board for all kinds of things, well, they're perfectly acceptable to also use in Vcore. And so that's what pretty much every motherboard manufacturer does. And that's why typically the output, like the bulk output filtering capacitors of really any motherboard VRM are going to be like 6.3 volts, 560 microfarads. And then the hour rating just kind of depends on how much you decided to spend on your motherboard. Your budget boards will use like 5,000 hours. Your high-end boards will use 10,000 hours, 12,000 hours. Doesn't really make a difference. But yeah, so that's what's going on with the output, with the like what kind of bulk capacitors the ASUS is using. For Vcore, they have 7 of them, which I find kind of interesting because this is more bulk capacitors than the Crosshair X670E Gene has. And yeah, that's just kind of interesting that like this cheaper board has more capacitors. But then again, the VRM configuration between these boards is quite different. Like there's a different VRM controller, different power stages. I think the inductors might be different. The inductors on this thing are actually very high inductance at 470 nanohenries. And so maybe that extra capacitance is just to deal with the potential higher overshoot that you get with high inductance inductors like this. Because you just store more energy in the capacitors, and then when you have a load release transient, that energy needs to go somewhere. And that's what the bulk capacitors are for. Basically to deal with that. Anyway, so yeah, Vcore is like Vcore filtering is looks good. Yeah. And then for the SoC VRM, we've got 3 of the same, mill branded. I kind of suspect these are APAC probably. So let's just put APAC in brackets over here, which is a capacitor. Like this is a Taiwanese capacitor manufacturer that both Gigabyte and ASUS use a lot on like their more value-oriented motherboards. It's not even budget these days. Like you'll find APAC capacitors on even some pretty expensive motherboards. Actually, this board's like $300. So, yeah. Well, the thing is, these aren't branded APAC, so I actually don't know for sure that they're APAC, but I would not be surprised if they were. Unless this is some manufacturer that I've never heard of. But anyway, so yeah, that's the Vcore output filtering is seven of these 560 microfarad capacitors. Then SoC is 3 of them. VDD MISC is 1 of them. Memory, we have 4 of them. So yeah. And memory filtering, like, honestly, I don't know if this is even necessary. But, yeah. So that's the output filtering configuration, and I don't really have anything to complain about. In fact, I'm quite impressed by the fact that we have all these extra ceramics on here. And now let's talk about the input filtering, which is the standard, like, ASUS motherboard affair of there's a lot of bulk capacitance for the input filtering. So you've got, for the, like, Vcore and SoC VRM, you've got 7... because you've got these capacitors over here, and then you've got these capacitors over here. These are all on the same power plane, right? So there's like an input filtering inductor over there. That's this square right here. So that's your input filtering inductor. Basically, 12 volts comes in from the 8-pin, goes through the input filtering inductor, and then gets distributed to, well, throughout the 12-volt power plane to all of the power stages and the capacitors, right? So that's what's going on with that. Anyway, so there's seven bulk input filtering capacitors, and those are all 270 microfarads, same branding, so mil, 5,000 hours at 105 degrees, and then 16 volts instead of 6.3 volts, because these are on the 12-volt power plane. If you put a 6.3 volt capacitor across a 12-volt power source, it explodes. Well, no, actually, it can explode. Like, I've done that. I did it with a 2.5 volt capacitor, which probably made the whole situation way worse. But yeah, like, basically, if you apply too much voltage to a capacitor, the voltage just punches straight through the capacitor. So yeah, that is one thing that, unfortunately, like, solid polymer capacitors are generally very robust, but if you overvolt them, yeah, they really don't like that. Anyway. These capacitors over here might look like they're part of the, like, Vcore SoC filtering. They're not. Those are all wired to the 24-pin, and they're for filtering the power for the rear I/O. So, yeah, as for why they're laid out the way they are, I have no idea. I guess I have no idea. They are covered up by the VRM heatsink, so I don't think... Like, the reason I bring this up is I've seen, like, some GPUs where they'll intentionally take their, like, input filtering inductor and they'll try to put it somewhere where it makes it look like it's part... And I think I've even seen motherboards do that, where you'll have, like, an input filtering inductor that's pretending to be part of the VRM to make it look like there's more phases than there really are. But I don't think that's what's going on here, because, like, these capacitors are normally covered up by a heatsink, so if I didn't point this out, I don't think anybody would have noticed. But yeah, these are wired to the 24-pin. They have nothing to do with the CPU power delivery. And that's a good thing, because, like, these are for filtering your, rear rear I/O ports. You don't really want your rear I/O to have VRM switching noise in its power supply, right? Like that would be bad. Anyway, another thing that ASUS decided that they don't really want VRM switching noise in its power supply is the VDD miscrail. So there's a little input filtering inductor before that, and then it gets its own bulk capacitor, which is just another one of these 270 microfarad 16 volt mill branded things. But yeah, I find it kind of interesting that they have like this extra input filtering inductor over here. And also what's kind of interesting is that they have the option to wire this to the 24 pin, right? Like this pad right here, that just goes off to the 24 pin power connector. So yeah, I find that kind of interesting that like they had that option. I'm not too surprised that they ultimately decided to wire it into the same 12 volt power source as everything else that powers the CPU, but yeah, kind of neat to see that, you know, there was a configuration option to run that off of the 24 pin. The memory VRM I already mentioned runs off of 5 volts from the 24 pin power connector. Is there anything else? Oh, right, memory topology. So this is a 8-layer PCB, which is pretty standard for pretty much, well, standard for like AM5 motherboards. There's very, very few AM5 motherboards with less than 8-layer PCBs. Even like, you know, even at around 200, actually, yeah, I think even down to $200, you still have a lot of 8-layer PCB boards. So yeah, this is an 8-layer PCB. It uses a shielded daisy chain topology. And what's kind of interesting to me is this is actually the first shielded, well, yeah, first shielded daisy chain topology that I've seen from ASUS, though, like, they are using this topology on all of their AM5 boards. It's not, like, special for this AM5 board. It's just special in the grand scheme of ASUS motherboards because most manufacturers were doing shielded daisy chains with, like, DDR4, and ASUS was still running their, like, this memory channel on the top layer of the PCB. For the longest time, like, you could see the entire memory channel on the top layer of the PCB, and that's no longer the case. There's just a great big ground fill over everything now, right? Like that's why you can kind of see the edge of it right there. So yeah, like the actual data queue is just buried further down in the board, though the command address bus we can actually see on the back of the board. At least parts of it, right? Like you can see all of this and all of this. Also, at one point in time, I thought ASUS was using the VD. So right here, this is not ground. Like this, yeah, like this thing right here, that's not ground. That's the VDDIO MEM power plane. And at one point in time, I thought like, oh, they might be using that as a reference plane for the like data queue. They are not doing that because this part of the PCB is ground again. So I'm guessing that the actual data queue for both memory channels is like pretty deep inside the board. Because yeah, it doesn't make sense to me that you'd have like different, like you wouldn't want to run your data queue for one half of the memory stick over the VDDIO MEM power plane and then the other half of it over ground. That just doesn't seem like a good idea. Like maybe the memory controller is able to account for that kind of thing, but probably, you know, like probably shouldn't be doing that. Also, there's just like an empty space right here, so like this isn't even like a full ground shield, so the data queue on this board has to be like, well, I mean, going from the top, right, we have like the first layer where we have the ground fill over everything, so we can't actually see any of the data queue, but you can have the data queue directly below that, and then you could have the next memory channel below that one, and then you could have a ground, like actually at that point you'd be at layer 4, so layer 4 could be just a bunch of ground or something. Or it could be on like layer 8, wait, no, 8, 7, it could be on like 6. Right, like one of the memory channels could be on like layer 6, one of them could be on layer 1, I mean layer 2, but yeah, unfortunately we're never going to get to see a motherboard in that much detail because the memory topologies are actually sort of, one of those things that the motherboard manufacturers like put a lot of work into and tried to keep to themselves. Yeah, so this is the, like, ASUS is now doing shielded daisy chains on their at least some of their motherboards. I've not checked if they do this on Z790 yet, but they have started doing this for AMD motherboards. It might also be like a recommendation from AMD, like, hey, our memory controller works best with this kind of memory topology, so you should implement this kind of memory topology. Or at least, like, it could, or something like, we've configured the memory controller to work with this memory topology, so if you don't do this, it's not going to work properly, right? Like, that's also a possibility. So, yeah, anyway, so the memory topology isn't anything, like, it's a daisy chain on an 8-layer PCB. That's basically, like, as far as I know, that's every AM5, like, pretty much, well, there are 6-layer AM5 motherboards, and there are higher layer count AM5 motherboards, but the vast majority of AM5 motherboards are 8-layer daisy chains. Also, the 8-layer PCB does help with power delivery, right? You can just have more, like, more layers dedicated to just power and ground. Also, it helps spread the heat from the VRM because there's just more copper in the PCB. But yeah, also the significance of the daisy chain topology is that you have to use the very last memory slots, which there are even some T topologies that require that. And the other thing is, well, the thing is, the Ryzen memory controller right now is in a weird state where it really, like, 2x16 and 4x16 perform very similar, like, don't really have a big difference between them. I don't have any I don't have any 32 gig DIMMs of DDR5 yet, so I don't know how that works. And 4x32 doesn't work well because you just hammer the memory controller when you have that many memory ranks. So, yeah, and that's not really like a topology thing. That's just like there's too much RAM connected to the memory controller. And it's not a capacity thing. Like, if you did 4x8, like 4x8, which you, yeah, actually you could do that. Well, you could do 4x16 in, like, with dual rank DIMMs that don't exist because it would be a dumb idea, but you could theoretically have a 4x16 configuration that's just as hard to run as a 4x32. It's just nobody makes the memory sticks that you would need to do that, which is a good thing because that would be really terrible if you, like, accidentally bought 2 kits of frickin' dual rank 16 gig DDR5. Now, that would be awful. Anyway, so yeah, that's it for this video. Like, looks like a solid B650E motherboard, which, like, the thing is, that's most B650E motherboards. Like I mentioned, like, there is a lot of overkill VRMs out there, though this probably might be one of the better ones in terms of voltage regulation. Just, like, yeah, just based on the, like, well, it's not even based on the extra output filtering capacitors, but, like, ASUS does put, like, does give their VRM tuning a bit more attention than some of the other manufacturers. Yeah, but I've not measured the voltage regulation on this board yet, but I really, like, honestly, I would be most surprised if it was, like, well, I'd be really surprised if it was bad. Very surprised if it was bad. I wouldn't necessarily be too surprised if it was actually, like, on par with the X670E Gene. Yeah, I wouldn't necessarily be too surprised if it was really close to the Gene in terms of performance. Anyway, so yeah, that's the ASUS Strix B650E-F gaming Wi-Fi motherboard. If, like, it'll run a 7950X just fine. At least it should. Again, I haven't gotten around to testing it yet, but I mean, with what we're looking at here, I'd be surprised if it had any issues. So, yeah, that's it for the video. So thank you to ASUS for providing the motherboard. And thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp, if you like industrial noise type stuff. So yeah, there's a link to that down in the description below as well. That's it for the video. Thanks for watching, and goodbye.